All right, section 1.6 is called the formal definition of limits. So what we have done so far with limits is we've sort of given an intuitive description of what we do. It's this value we get close to and we may or may not touch. That's not very mathematical. That's a very touchy-feely sort of sentence already. So what we're going to do in this section is we're going to put some nuts and bolts, some like real concreteness to our definition of limit. In order to do that, we're going to talk in general about how we get from that sort of generalized picture we have in our mind to that concrete picture that we want to have. So we're going to consider this function f of x equals 5x plus 2. And there's some space on your paper if you'd like. Go ahead and draw what that equation would look like. It is an equation of a line. Where does it cross the y-axis? At 2. Okay. And it has a slope of 5, so we go up 5 and over 1. Something like this. And if we're successful, we connect them, it looks like something like this, like a line. All right, good so far? We're going to try and find the limit as x approaches 3. Now, my picture isn't even very good because I can't even get to 3 on my picture, so let me change what I've done just a little bit and make it a little bit bigger where I want it to be. So there's that x value of 3, cross at 2. My graph looks something like, I'm doing it red. This. No. That's better. All right, so what we want to do is we want to find the limit as x approaches 3. Now we know from section 1.3 that we can actually just plug in the number and this works just fine. So if we plugged in the number 3, we'd get 5 times 3 plus 2 and we get 17. All right, so we know from algebra operations, if you will, that we're going to get 17. Okay, this intuitively makes sense to us. This description, however, is imprecise, like I mentioned, and we're going to consider this graph. So I'm going to keep, you've got your notes with you, I'm going to keep reading. I know it's in another slide here, but I'll get there in a minute. So let's say that we want to make sure that the function value, that's the y value. Okay, so when we see function value here, it means the y value. And the limit of the function as x goes to 3 are close to one another. So occasionally that doesn't happen, right? You think about graphs that have jumps in graphs. The function value and the limit value don't necessarily have to be the same. Okay, so if we want to make sure that they are very close to one another, and perhaps, for example, we want them to only differ by 1 unit. So over here at x equal to 3, I'm about right here. We'll hope that that's at 17 over there on the y-axis. Yours is probably going to be better than mine because I'm eyeballing it a little bit. But at about x equal to 3, we're looking at this point in particular right here, and let's just say for the argument's sake that that's 17. Don't count them because I'm probably sure it's not. Okay, just pretend for a moment it is. I probably should have just marked it without all the hash marks. That would have been better. All right, so what we want to know is we want to know if we only have the y value and the limit value differ by 1. So that means like we were within 1 unit here. So we only go up 1 from 17 and down 1 from 17. So we're sort of between 15 and 18, right? We're within 1 of the y value. How close would our x value need to be to the number 3 to make that happen, for sure? That's the question. How tight in here? Would it also be 1 across here? Would it be between 2 and 4? Or would it have to be tighter? So that's what we're looking at here is how tight do I need to be around the x value of 3 in order to make sure that I'm really tight around the y value of 17. Okay, so do you have an image in mind of what we're doing? We're trying to tighten up the area, looking very, very, very close, like zooming in and zooming in and zooming in, and figuring out if we continue to zoom in around this point, and we looked sort of like at the x-axis and the y-axis, what's the ratio here? What's going on? How close do I need to be? Okay? So let's take a look at this one in particular. If I wanted to be within 1 unit, right, I said that I wanted to go between 16 and 18, then that means I want my function itself, that's the graph 5x plus 2, and the limit value, this is the limit value, we want their difference to be less than 1. Okay? The difference is how we create something that's talking about how far apart they are. How far they are apart is going to be less than the value 1. So we need to figure out what in the world we would have to do to create this around the x value of 3. So my question is, what do I need to do? How close to 3 do I need to be in order for that to really happen? So what we're going to do is we're going to do stuff from college algebra, and we're going to solve this inequality right here that we just created. 5x plus 2 minus 17 is less than 1. So we're going to simplify inside of the absolute values first. So what do I have if I simplify inside my absolute values?
5x minus 15.
Perfect. 5x minus 15. Everybody good with that? Okay. Now considering the 5x and the minus 15, do they have anything that we can in common to factor out?
5.
A 5. So I'm going to write it like this. Does that look good? Now, a property of absolute values is that I can separate this absolute value like this. And we know that the absolute value of 5 is 5. So that's just going to be 5 on the outside. And then x minus 3 here, less than 1. And then remember our goal here, where we want to get to is the x minus 3 absolute value. And it's there now, right? We have it. What do we have to do to get a loan? Divide by 5. So this x minus 3 absolute value now is going to be less than the number 1/5. So I heard some of you saying when I asked the question, like, can I just go between 2 and 4, like 1 apart on the x-axis? Is that going to be far enough, close enough? I heard some people going, shaking their head, no, it's not going to be close enough. It isn't. I have to be within 1/5. So the furthest away I can go in either direction from the value 3 is 1/5 in each direction. So basically I can go up to 3 and 1/5, or I can go down to 2 and 4/5. That's as far away as I can be on the x-axis and still be within 1 on the y-axis. Any guess on this one as to why that number is becoming 1/5? It's the slope of this particular function. Now we're not always working with lines, but when we are working with lines, it does come into play. So that is because of the slope. Now notice though, what we did here is that we chose this value of 1. And it was rather arbitrary. I just said, hey, let's go between 1 away from the value 17 on the y-axis, didn't I? I said, let's just say we want to be within 1. Well, that was rather arbitrary. I mean, I could have said we want to be within the value 1/2, or we want to be within the value of 0.10 or 0.10 or something like that. I could have said any number. So instead of saying I could have said any number, we're going to do exactly that. We're going to give that number a name, and that number's name is epsilon. Okay? So epsilon is just a really small number, and it's positive. That's all it is, a small positive number. And we're going to do the same thing. You notice this equation looks exactly like it did on the other screen, except what? The epsilon, where I previously had a 1. That's the only difference. And now think back over here. Did I really do anything with the 1? No. In fact, I didn't even touch it. I just kept rewriting it the whole time, didn't I? Well, that's the same thing that's going to happen with epsilon. So if we took this equation, or inequality, excuse me, we would solve it in very much the same way that we just did a moment ago. It's just that it's going to have an epsilon on the right-hand side. We're going to factor, and we're going to write it like this, and then we're going to end up recognizing that that, of course, is a 5, and recognize that we can divide then by 5. And we get right here in this blank the number epsilon over 5 instead of 1/5 like we did just a moment ago. Now, we give this blank spot a name, just like we gave this arbitrary value here a name, epsilon. The name for this blank spot right here is the name delta. Okay, so this right here has the arbitrary name, not arbitrary, but it has the name delta. So what we've just found is we've just found that the delta value equals epsilon over 5. You will hear what we're doing here called epsilon delta proofs. Now, I haven't actually proved anything yet. I've just shown you how in the world we find out what is delta, right? We've figured out what in the world is delta. So I need to show you then what you do once you figure out what delta is, and we'll do that on a specific example. Okay? Now, before we can get to the example, I want to show you where the proof part comes from. And it comes from this precise definition of limit. So go ahead and fill in the blanks first, and then we'll talk through about what this says. Okay, is everybody pretty well done writing? Excellent. All right, so first of all, let me make one comment about this, is that I need you to memorize this. I'm going to ask it to you on your test on Friday. This is on the review sheet, verbatim. I want you to be able to say this statement verbatim, with all the details in there just like they are. Okay, so just flat out memorize it. It's an easy number of points because I'm telling you something that's on the test, so that's a good thing, right? All right, so this says, for a function f, defined on some open interval containing a. So let me draw a picture of what it's telling you. You've got a function, and it looks like something, and you've got a value a, and it's defined at least somewhere close to the value a. All right, so it may be doing weird things otherwise. This particular one doesn't look like it's doing weird things, but it could be. So it's defined everywhere nearby a. It might not actually be defined at a itself. Then we can say that the function value, the limit value of the function equals L. Here's my L. If for any epsilon greater than 0, so any epsilon I pick in here, any distance here that I pick epsilon, I wrote the wrong one, epsilon, then it corresponds over here to another distance right here, delta. This is exactly what I did in the picture, right? I can pick anything far apart or close enough or whatever around the value L, and it will correspond to a little bitty interval around the value a, so that when we are within delta of the value a, we're going to for sure be within epsilon of the value L. As long as I'm really tight and close around here, I'm guaranteed to be tight and close around the limit value. There can't be any sort of wildly crazy oscillating function going on nearby this particular value and the limit value exist. That's what that's saying. Okay, if we get close enough, we can always do it if the limit value exists. Now, when we write our proofs, they're going to look very much almost like mimicking this definition. So you've got, what do I have, 6 of them on your homework that you're going to do like this. After you've written the proof for this 6 times, which is basically what you're going to end up doing, you're going to be very comfortable with this definition because you will have written it pretty much 6 times. So let me show you how this works. We're going to create, we've got an equation. This one's very, very similar to the one I just did, but I haven't actually finished the process with the one we just did. So let's start with this one. It says first, symbolically find delta in terms of epsilon. And then over here, afterwards, we're going to write the delta epsilon proof. Okay? So that was left off. All right, so what do? Well, we set up an absolute value. The absolute value has the function, in this case 3x plus 2, minus the limit value, so minus -4, and we set it up to be less than epsilon. And we solve this inequality. All right? So somebody simplify what's inside the absolute values for me. What is it?
3, and then the absolute value of x plus 2.
Okay. So let me take one step before you did that. Did you have 3x plus 6 first?
Yeah.
Matt? Okay, good. And then you factored out a 3, right? Okay, good. And then when you factored out a 3, you add x plus 2?
Yes.
Excellent. Now, it's important that Matt got x plus 2, and of course that you did as well, because this x plus 2 better match the fact that the x is approaching negative 2. Because this is supposed to be x minus that value, which is negative 2. So I mean, this is what I'm supposed to be getting. Okay? So it does, in fact, match that, right? Because x minus negative 2 would be x plus 2. So it is matching. So then my last step would be then to do what?
Take the 3 over.
Right. So this is saying x plus 2 is less than epsilon over 3. What this is then is this is delta. Okay, that's what we did. So the first directions that were typed on your paper already, we did those directions. We found delta in terms of epsilon. Okay. What we're going to do next is we're going to use that information to actually write the proof that goes along with this. Okay. So it's going to say something like this. We can say the limit as x approaches negative 2 of 3x plus 2 equals negative 4 because for any number epsilon greater than 0, there exists a delta equal to epsilon over 3, such that 0 less than x plus 2 less than, you know what, let me move this down, less than delta, which is equal to the epsilon over 3. I don't know why I want to make it over 4, but I do. Epsilon over 3 guarantees that 3x plus 2 minus negative 4 is less than epsilon. And they all have this form. We can say that this is the limit value. We know that this is the limit value. It is true that this is the limit value. Because anytime we take an epsilon, there's this delta. And this delta in this case is equal to epsilon over 3. So that when our x value is very close within that epsilon over 3 of its value, the number 2, negative 2 in this case, then the y value, the function value, is going to be very close to the limit of negative 4. Okay? And we do get epsilon over 3, right? Just like we thought we would because we had the 3x plus 2. The slope was 3, right? All right, let's try another one that doesn't quite look so clean. It's not a line. Same directions as before. We're going to write a proof at the end. So I will ask you to do one of these with a proof on your test. So you might as well take the opportunity to do a proof for every single one in your book, whether it says to or not, so that you're very well versed and comfortable of doing it when you get to it on Friday, okay? All right, so the process still works the same. We take the absolute value of our function. In this case, it's x squared plus x minus 2 over x minus 1. And we subtract the proposed limit value, which is 3. And we set it less than epsilon. Now what? Factor and reduce. That's a very good step if you've got a fraction. So let's try that. How will this factor? X plus 2, x minus 1, which is awfully nice, right? Because what happens? The x minus 1 cancels. So this particular function is actually not defined at x equal 1, is it? I cannot plug in the number 1 into this function. So back in those directions right here, or the definition, it says, but not necessarily at a itself. This is an example of the not necessarily at a itself. It is not defined at a. But it's defined as close as we possibly want to get to that value. Okay? All right, back over here then. We are to the point where we've got x plus 2 minus 3 is less than epsilon. So what do I get inside now? X minus 1. And that's what I want, isn't it? How do I know that that's what I want? Because this limit is going to be the limit as x approaches 1. So this value down here has to say x minus that x value, x minus 1. Perfect. Now, what's cool is that we were supposed to be finding delta. There's not any division or anything to do on this particular one, right? So what do you think that might mean here? Perfect. Good job. That's right. Delta equals epsilon. Whenever I get to the point that I've got the x minus the limit, or the limit x minus the x value that I'm approaching for my limit, then whatever is left over here, in this case it's just epsilon, that is my delta value. All right, so now we're going to write the proof that goes along with it. And we'll just change up the language a little bit as we go, because I don't want you to think that my specific language is something super special. There's pieces of what I'm writing that have to be there, but there's other pieces that you could change. For instance, we could say something like, it is true that the limit of x squared plus x minus 2 over x minus 1 as x approaches 1 equals 3, because for every epsilon greater than 0, that's the part you can't skip out on. That part has to be there. Every epsilon greater than 0, there exists delta, in this case, equal to epsilon. Okay? Such that when 0 is less than x minus 1 is less, I did this last time, I ran out of space, right here at this exact same spot, is less than delta equal to epsilon, or you could just say delta there or epsilon there, it would be okay, but they're equal. Then the function x squared plus x minus 2 over x minus the 3 is less than epsilon. Just a couple of common things that I want to draw your attention to. This is for every epsilon, and this is there exists a delta. If you switch that language, it actually means something quite different. So that language in that order is very important. It is for every epsilon there exists a delta, not vice versa. Okay, so that part of it is very specific. And it comes straight out of the definition, right? The definition says for any number epsilon, there has to exist another number delta. So that's part, I mean, it's mimicking that definition back in it when you're doing it. All right.